In this lecture, we're going to talk about how to solve a special type of first-order differential equation called an exact equation. So to begin with, a differential expression of the form m of xy dx plus n of xy dy is called an exact differential in a region R of the xy plane if it corresponds to a differential of some function f of xy defined in R. A first-order ODE of the form m of xy dx plus n of xy dy equals 0 will be an exact equation if the left-hand side is an exact differential. All right, so to show that something is an exact differential, we can use the following criteria. Let's let m of xy and n of xy be continuous and have continuous first partial derivatives in that rectangular region R, defined by a is less than x is less than b, and c is less than y is less than d. If this is the case, then a necessary and sufficient condition that the expression is an exact differential would be that the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. So essentially what we're doing here is we're looking at some function of two variables, x and y. So f of x and y. And if you've taken Calculus 3 and you've learned about taking partial derivatives, you know that you can take the partial derivative of f of xy with respect to x or with respect to y. So if we have some function f of xy and we've taken the partial derivative with respect to x, that's given us the m of xy from our differential equation. And when we take the partial with respect to y, that gives us the n of xy from our differential equation. All right, we can continue taking the partial derivatives and find what's called the mixed partial by taking the partial of m with respect to y and the partial of n with respect to x. So that leads us to the mixed partial of f with respect to x and y. So again, from Calculus 3, you learned that when you take a mixed partial derivative, it doesn't matter which order you take it in. So you could do the partial of x and then the partial of y, or you could do the partial of y and then the partial of x. Either way, it should give you the same result. So when we're looking to see if a function is an exact equation, we're given these two terms, m of xy and n of xy, and we're trying to show that when we take those partial derivatives, it leads us to the mixed partial of f. So that'll prove that there was a function of f, which we can find as our solution. So for example, if we want to show that something is an exact equation, we're given 1 plus the natural log of x plus y over x dx equals 1 minus the natural log of x times dy. If we want to determine if this is exact, the first thing we'll need to do is we'll need to write it in the potential form m of xy dx plus n of xy dy. So we'll subtract the dy term over to the left-hand side. That gives us 1 plus the natural log of x plus y over x times dx minus 1 minus the natural log of x times dy is equal to 0. Now that it's written in the correct form, we can examine our m and our n. So m is 1 plus natural log of x plus y over x, and n is negative 1 minus natural log of x. We can examine the partial derivatives here. So we take the partial of m with respect to y. So if we look at this, our first term doesn't contain a y, so that gives us a 0. Our second term here also doesn't have any y's in it, so that gives us 0. And the derivative of y over x with respect to y will just be 1 over x. Then if we look at n, so the function n, we want to take the partial of n with respect to x. So first thing we'll do is we'll distribute the negative sign throughout to get negative 1 plus the natural log of x. And then when we take our partial derivative, there are no x's in negative 1, so that gives us a 0. And then the derivative of natural log of x is 1 over x. So we can see that the partial of m with respect to y is the same as the partial of n with respect to x, and that shows that this equation is exact. All right, so once you've shown that an equation is exact, you can take the following steps to solve it. The first thing we're going to do is we'll start over here on the right-hand side of our diamond. So we're going to take m, and we're going to use it to find f. So to move up the diamond, we need to take the integral. So we're going to integrate m with respect to x. That's going to give us the f that we're looking for. And keep in mind that when we integrate, the arbitrary constant that we normally add might be a function of y. So when we add the arbitrary constant, instead of adding a c, we'll add something like g of y or h of y to account for the fact that there might have been a y in that constant. All right, after we figured out what f is, we'll come down to the other side. So we'll come down over here. We'll take the partial derivative with respect to y. So we take the partial derivative with respect to y. And then since we're over here on the right-hand side of the diamond, that partial derivative should be equal to n. So if we set the partial of f with respect to y equal to n, that's going to allow us to solve for that arbitrary constant or that arbitrary function. Right? And then finally, we'll set that solution equal to c to get our overall answer. So let's put that to the test. We're going to go ahead and solve an exact equation. We're going to continue the example that we had previously started. So we had 1 plus the natural log of x plus y over x dx minus 1 minus the natural log of x with respect to dy, 1 minus the natural log of x dy is equal to 0. So if we want to solve this, we've already shown that it's exact. If we want to solve it, we're going to start by taking the integral of m with respect to x. So the function we're looking for, f of xy, will be the integral of 1 plus the natural log of x plus y over x dx. If we integrate this, we're going to get f of xy equals x plus x natural log of x minus x plus y times the natural log of x. And then we'll add our arbitrary function g of y. We can simplify this term. We see that we have an x and a minus x, so those will cancel out. So f of xy will be x times the natural log of x plus y times the natural log of x plus g of y. So this is what our solution is going to look like. Now we need to figure out what g of y is. So to do that, we'll take the partial derivative of f with respect to y. So if we take the partial with respect to y, there's no y in this first term, so that gives us a 0. Y times the natural log of x, we treat natural log of x like it's a constant, so the derivative would just be natural log of x. And then the derivative of g of y will be g prime of y. So we have the partial of f with respect to y is the natural log of x plus g prime of y. We're going to set that equal to n. So natural log of x plus g prime of y equals -1 plus the natural log of x. And we'll see that we have common terms on both sides of the equation. So those natural log of x's, they'll cancel each other out. And that means that g prime of y has to be -1. To find g of y, we're going to integrate this. So g of y will be the integral of -1 dy. So g of y is going to be -y. And then to finish things off, we'll say f of xy equals x times the natural log of x plus y times the natural log of x minus y plus c. Or we could say c equals x natural log x plus y natural log x minus y. So that'll be the solution to this exact equation. All right, let's look at a second example. So for the second example, we want to solve 5y minus 2x times y prime minus 2y equals 0. So the first thing we need to do is write this in the form where it's a potential exact equation. So we can rewrite y prime as dy dx. So 5y minus 2x times dy dx minus 2y equals 0. And we'll multiply everything by dx. So 5y minus 2x dy minus 2y dx equals 0. So now this is in the form where it's potentially an exact equation. So we need to look at m, which is -2y. Remember, m is always paired with dx. So even though this is written in a different order, we always take m to be the term that's with dx. So m is -2y, and n is 5y minus 2x. We take the partial derivative of m with respect to y, and that gives us -2. We take the partial derivative of n with respect to x, and that also gives us -2. So since we get the same partial derivative with respect to y of m, and the partial derivative of n with respect to x, since those two are the same, that shows that this is an exact equation. And that means we can use the method for solving that we're talking about in this section. So we're going to start with our m, and we're going to integrate it with respect to x. So our function f is going to be the integral of negative 2y with respect to x. So since negative 2y doesn't have an x in it, we treat that like it's a constant. And so the integral will be negative 2xy. And then we add our arbitrary function g of y. So now we have our potential solution, our potential function f. We need to figure out what g of y is. So we'll take the partial derivative with respect to y. And that's going to give us negative 2x plus g prime of y. And then we'll set that result equal to n to figure out what g prime is. So if the partial of f with respect to y equals n, then that means negative 2x plus g prime of y equals 5y minus 2x. We see we have a negative 2x on both sides, so they'll cancel out, which means g prime of y has to equal 5y. To find g, we'll integrate both sides. And so that's going to give us g of y equals 5 halves y squared. All right, our final step is to plug that back in. So f of xy will be negative 2xy plus 5 halves y squared plus c. And we can move the c to the other side. We'll set f equal to c to get our final solution. C equals negative 2xy plus 5 halves y squared. All right, let's look at a third example. So this time we have 2x plus y dx minus x plus 6y dy equals 0. So if we look at m equals 2x plus y, and n is a negative x minus 6y, if we take our partial derivatives, the partial of m with respect to y is equal to 1, and the partial of n with respect to x is equal to negative 1. These partial derivatives don't match, they're not the same, and so that means this is not an exact equation. All right? So what do we do if we encounter a problem that's not an exact equation? Well, it is possible to transform a non-exact equation into an exact equation using a different integrating factor. So here's the situation where that would work. If the partial of m with respect to y minus the partial of n with respect to x divided by n simplifies to be a function that only involves x, then we can use the integrating factor mu of x equals e raised to the integral of the partial of m with respect to y minus the partial of n with respect to x divided by n times dx. If we rearrange things, if we take the partial of n with respect to x minus the partial of m with respect to y and divide that by m, and we get a function of y alone, then we can use the integrating factor mu of y equals e to the integral of that expression. So the partial of n with respect to x minus the partial of m with respect to y divided by m and times dy. Now let's look at an example where we're going to transform a non-exact equation into an exact equation. We have the problem yx plus y squared plus y times dx plus x plus 2y times dy equals 0. So the first thing we'll do is we'll check to see if this is exact. So our m is yx plus y squared plus y, and our n is x plus 2y. We take our partial derivatives. The partial of m with respect to y is going to be x plus 2y plus 1, and the partial of n with respect to x is just going to be 1. These do not equal each other, so clearly this is not an exact equation. So we'll try to find an integrating factor. So we have two forms of an integrating factor from our previous slide. Let's look at the partial of n with respect to x minus the partial of m with respect to y divided by m. If this simplifies to be a function that only has y in it, then we could use it as an integrating factor. So we found these values above. The partial of n with respect to x is 1. The partial of m with respect to y is x plus 2y plus 1. So if we plug those in, we get 1 minus x plus 2y plus 1 divided by yx plus y squared plus y, so that was our m. If we simplify this, in the numerator, those 1's will cancel out. So we get negative x minus 2y divided by yx plus y squared plus y. Now this is not a function of y alone because we have x's in there, so this isn't going to work. So let's look at the other formulation. We have the partial of m with respect to y minus the partial of n with respect to x divided by n. So if this results in a simplification that is a function of x alone, so there are no y's, then we can use this to form our integrating factor. We plug things in, so the partial of m with respect to y is x plus 2y plus 1, and the partial of n with respect to x is 1. So we get x plus 2y plus 1 minus 1 divided by x plus 2y. Our 1's up here in the numerator will cancel each other out, so we're left with x plus 2y over x plus 2y, and so that'll simplify to give us 1. There are no y's in this simplification, so this is a function of x alone, or a constant, so we can use this to form our integrating factor. Our integrating factor is going to be e raised to the integral of that result, so e raised to the integral of 1 dx, which is going to give us e to the x. Now we multiply everything by our integrating factor, e to the x. That gives us yx e to the x plus y squared e to the x plus y e to the x dx plus x times e to the x plus 2y e to the x times dy equals 0. Now if we examine this, m is equal to yx e to the x plus y squared e to the x plus y e to the x. If we take the partial derivative with respect to y, that's going to give us x e to the x plus 2y e to the x plus e to the x. And then if we look at our n, x e to the x plus 2y e to the x, we take the partial of that with respect to x, we'll get x e to the x plus e to the x using the product rule on that first term, and then 2y e to the x from the second term. Well, we can see that these two partial derivatives are the same, so our integrating factor has transformed our problem into an exact equation. So now that we know that we have an exact equation, we can go through and solve using the approach that we've talked about in this section. So we're going to integrate m, so we take the integral of yx e to the x plus y squared e to the x plus y e to the x with respect to x. That's going to give us yx e to the x minus y e to the x, so that's using integration by parts on this first term, plus y squared e to the x plus y e to the x plus our arbitrary function g of y. Now we can simplify this. We have a minus y e to the x and a plus y e to the x, so they'll cancel each other out. So we get f is equal to yx e to the x plus y squared e to the x plus g of y. We want to figure out what g of y is, so we'll take the partial derivative with respect to y. That's going to give us x e to the x plus 2y e to the x plus g prime of y. We set that equal to n, so x e to the x plus 2y e to the x plus g prime of y equals x e to the x plus 2y e to the x. We have those common terms on both sides, so they'll cancel out. So g prime of y is equal to 0. So if we integrate that, that means g of y is just going to be an arbitrary constant c. And so we can put that into our solution. C is equal to yx e to the x plus y squared e to the x. And that'll be the solution to our differential equation.